In this video, we'll draw some Lewis structures of compounds that have single bonds, double bonds, and triple bonds. If I look at number 1, C2H4, you always want to start with the atom that can make the most bonds, which if there's a carbon in the compound, carbon makes 4 bonds, which is the most that we'll ever deal with. So we're going to put the carbons down first with their 4 valence electrons. 3, 4. Carbon 1, 2, 3, 4. Now obviously I somehow need to bond these 2 carbon atoms so we can link them up in the middle. And I have 4 hydrogens. However, I have 6 spots that still need a bond. Well, we try to be fair to both carbon. And if we have 4 hydrogen, we'll go 2 on each. You could put those 2 hydrogen anywhere. So I could go hydrogen on the side. I could put a hydrogen on the top. I could put this one up on top. And I could put another one over here. And I can connect the dots and make some single bonds. A single bond is the sharing of 2 electrons. A double bond is the sharing of 4 electrons. Can you see what's going to happen to the carbon? They each have 1 extra valence electron, and there's nothing else to bond. So we'll just bond them to each other. Here's your double bond. 4 electrons shared between the 2 carbon. Something like CO2, carbon dioxide. I probably want to start with the carbon again. There's only 1 carbon atom, and he makes 4 bonds. 4. I got the 2 oxygen, and we said, yeah, we want to try to pair up the single electrons. We know that's where the bonds usually form. So we'll go the 2 singles and the 2 pairs on oxygen for a total of 6 valence electrons. Okay, so we have to bond them at some point. There's a single bond. Do you see the double bond? The oxygen needs 1 more bond. The carbon can take another. We'll double bond the oxygen. And we can do the same thing with the other oxygen. We'll line up the singles. So the singles might look a little different, but that's okay. Cool. We'll line up those single bonds, or single electrons, so that we can link them up once. We can link them up twice. And there are your 2 double bonds in carbon dioxide. And everyone has an octet. Carbon has 2, 4, 6, 8. All 8 are bonding electrons. Oxygen has 4 bonding electrons and 4 non-bonding electrons, or lone pairs. Carbon can do all kinds of bonds as long as he gets a total of 4. So your options with carbon, you could do 4 single bonds. Carbon can do a double and 2 singles, like in number 1. Carbon could do 2 double bonds, like in number 2. Or check out number 4. Carbon will go in the center with his 4 valence electrons. 3, 4. We'll link up the hydrogen with only 1. And we know that's going to be a single bond. Hydrogen cannot double bond or triple bond. He only wants 1 bond. And now normally when I draw my nitrogen, I put the lone pair on the top, and then I have 3 singles for a total of 5 valence electrons. But it really doesn't matter where you put the singles or the pairs. So now on this nitrogen, I'm going to kind of purposely line up the singles so they match with carbon. And then I'll put the pair to the outside. Do you see a triple bond? A triple bond is the sharing of 6 electrons. 1, 2, 3. So here are your options with carbon. 4 singles, 2 doubles. We could do a double and 2 single, or we could do a triple bond and a single bond. Carbon can do it all. Now earlier when we were doing periodic trends, we were talking about some of the diatomic elements. They exist as two atoms covalently bonded together in nature. And at the time we said, just remember which ones are covalent, and later on, when we get to bonding, we can figure out why. So let's say you have two nitrogen atoms. Nitrogen, nitrogen. And again, I know they're going to bond toward the center, so I'm going to put my 3 single electrons, again, toward the middle. I'll put my pair on the outside. I want my 3 single electrons to bond. We have another triple. We can link them 1, link them 2, link them 3. Nitrogen likes to triple bond to himself. It's a match made in heaven. You got a whole bunch of nitrogen atoms hanging out together. They each need 3 bonds. Well, why don't we just bond with each other? Let's just share a triple bond with each other. The sharing of 6 electrons. Similar situation, let's say number 6, O2 oxygen. O2, diatomic oxygen. Oxygen with his 6 valence electrons. 5, 6. And 1, 2, 3, 4, 5, 6. Oxygen likes to double bond to himself. We can connect the dots once, connect them twice. The sharing of 4 electrons. Again, oxygen is a very stable diatomic molecule. Each oxygen needs 2 bonds, so they'll just double bond to each other. The halogens are all diatomic for kind of the same reason. You've got fluorine with his 7 valence electrons. Fluorine. 1, 2, 3, 4, 5, 6, 7. So we'll link them up and do a single bond. The halogens will only single bond. Halogens and hydrogen. They only want 1 more bond. Hydrogen and halogens are very stable diatomics for that reason. If they each need 1 more bond and there's a whole bunch of fluorine atoms close to each other, they can just share with each other. Now between a single bond, double bond, and triple bonds are the strongest. They will require the most bond energy. The energy required to break a bond. It's the sharing of 6 electrons that would need to be separated versus 4 or 2 in a single bond. And so again, we've got 5 and 7. Carbon will probably go in the center because he makes the most bonds. 3, 4. I can put on the hydrogens, and technically you can put these hydrogens anywhere. I'll just throw them kind of on the sides, and we'll only consider single bonds with our hydrogen. And then perfect. I have 2 more single electrons that I'll link up with the single electrons of oxygen. 2 singles, 2 pairs for a total of 6 valence electrons. We can double bond the oxygen. Everyone has an octet. 2, 4, 6, 8 bonding electrons on carbon, 4 bonding electrons, and 4 non-bonding electrons are on the oxygen, and hydrogen only needs 2. The last one, number 7, 2 nitrogen and 2 fluorine. Sometimes people try to get kind of creative on this one, but again, you want to start with the atoms that can make the most bonds. Nitrogen has 5 valence electrons, wants 8, will make 3 bonds. Fluorine already has 7, so he really only wants 1 bond. Your nitrogen will go in the center with the fluorine toward the outside. Hydrogen and halogens will always go toward the outside of the molecule. And again, we've got 5 valence electrons on the nitrogen. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. A pair and 3 singles. And I know I need to, at some point, link them together. Let's see what happens with these fluorine. 7 valence, So we'll put the singles toward the center and the pairs on the outside. Single toward the center. Here are my pairs on the outside. I got this now. We'll single bond the fluorine, and then each nitrogen still has one more electron. We can link them in a double bond. We'll double bond the nitrogen in the middle, and we'll single bond the fluorine on the outside. And usually by drawing these dot structures, you can predict single bonds, double bonds, and triple bonds, especially if you get the dots correct around the central atoms, meaning there's supposed to be a certain number of single electrons and paired electrons. Now in the next video, we'll look at a couple exceptions. There are a few times when this dot model doesn't give us a good prediction of the true Lewis structure. We'll look at those in the next video.